Okay, so good evening, everyone. I'm Karl Silverberg, and I'm going to talk about uh, the SETI program and the Fermi paradox. And so the question is, where is everybody? And it's estimated that there are about 100 to 400 billion stars just in the Milky Way galaxy. And the question is there intelligent life in the Milky Way galaxy? But just to start off with, I'm curious. I'm going to ask the question to the audience. Question one, raise your hand if you believe that life in the Milky Way, forget the universe itself, the universe is so large, it's almost infinite. Let's just take the Milky Way galaxy itself.
Getting a bad
High
echo.
probability versus low probability. How many people?
There's a bad echo because the computer that counts sensor
Yeah,
icon.
there is a microphone. Hello, 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 hello.
Everybody believe that it's low
Hello,
probability that
hello.
there's life in the Milky Way
They're
galaxy.
not gonna hear us.
Ken Spencer, turn your microphone off. It's echoing.
That's a good clarification.
Yeah.
Let's, for purposes of this question, let's just say it right now.
My answer then is no.
What?
My answer is no.
John
And myself are the only ones who believe low probability,
Disappointment.
which is a good
A good instinct.
because this subject was inspired by Brian Cox's book Human Universe. And you may or may not know Brian Cox. Brian Cox is a very popular astrophysicist who's written a lot of books and is often seen on like BBC programs on science. And he's done a lot of science television shows. And his take on SETI and the existence of life in the Milky Way galaxy is that it's probably a very low probability that there's life out there. And maybe after tonight's talk, you may have a different take on whether it's high probability or low probability.
So in June 14th, 1947, a very experienced civilian pilot named Kenneth Arnold reported seeing objects
in the sky while he was flying, and he reported it as
if they saw saucers skipping across the water.
That got reported in the newspaper as him seeing flying saucers. Soon after that, in July 1947, the Roswell event occurred, and the Army reported that there was a flying saucer in the sky, which the Army retracted and said, "Oh, it's just a weather balloon." But this gave birth to the whole flying saucer phenomena that we know today. And of course, the idea of people from outer space has been around for longer than that. In 1877, Italian astronomer Giovanni Schiaparelli, believed he was seeing canals on Mars when he looked at Mars. And of course, in 1898, H.G. Wells published War of the Worlds about an attack by Martians. That led to this interesting or funny cartoon that was published in the New Yorker in 1950. For some reason, in 1950, the garbage cans were disappearing off the streets of New York City. Someone published a cartoon that maybe it's aliens and their flying saucers coming to get these garbage cans. But
it just so happened that
this cartoon was brought up as a conversation piece among the world's top physicists who were sitting down to lunch at the Los Alamos Laboratory in New Mexico. And Enrico Fermi
famous first questions asked the question,
you know,
where
where
is everybody?
basically under the same presumption that we just had just now, where we all raised our hands saying, well, it's gotta be a high probability that there are other intelligent life forms out there, just given the size and the real estate out there. And he says, you know, he posed the question, you know, where is
everybody?
So first question to the audience, who is Enrico Fermi? Does anybody want to chime in?
Enrico Fermi
was one of the fathers of the Manhattan Project. 1938, he won a Nobel Prize at age 37. In 1941, he had the idea of using a fission bomb to ignite a fusion bomb, which he shared with his colleague Edward Teller, who was also at that 1950 table having lunch with Enrico Fermi. And Edward Teller went on to become the father of the hydrogen bomb. He was also the first person to build a nuclear reactor. That's what he's probably maybe most famous for. He created the first demonstration of nuclear energy. In a very similar way that we have nuclear energy today with graphite rods and graphite bricks. And he built the first sustained nuclear reaction in 1942, which was a very important stepping stone in the Manhattan Project. Another question to the audience: where was Pile 1? Where was Pile 1 located?
Under the bleachers.
Yes, it was under the bleachers at the Chicago Stadium, under an abandoned Chicago Stadium, University of Chicago in downtown Chicago. And you might, you know, that's the Army at the time and the local officials trusted that Enrico Fermi to handle it without it becoming a nuclear meltdown. So what was Fermi trying to say with this question? Based on conversations with the other people at the table, basically he was coming to the conclusion or making the observation that space is large and there might be a difficulty with distances that is preventing that might prevent communication between intelligent life forms. But since then, some people have taken it to mean that life does not exist beyond Earth. Then maybe there's a reason for the silence. Maybe the silence is because it's very difficult to form life. But the 1420 marker was a frequency that's a radio frequency emitted by hydrogen, which people speculated might be a universal radio signal that other intelligent life forms might use because hydrogen is so prevalent. And in fact, subsequent to that, the 1420 megahertz frequency has been relegated to scientific research, and you're not allowed to actually use that signal in radio broadcasting because it is reserved for science, so that if we hear something, we know it's not ground-based. And in 1961, Frank Drake came up with this famous Drake equation, which we'll discuss in a little bit more detail. But the Drake equation says N is the number of detectable civilizations in space, and that's equal to R, which is the rate which new stars form, FP, the fraction of stars with planets, NE, the number of planets per star where conditions for suitable life exist, habitable zone planets, F1, the fraction of planets where life actually emerges, Fi, the fraction of life containing planets where intelligent civilizations develop, Fe, the fraction of intelligent civilizations that produce communication technology that we can detect, and L, which is somewhat of a sociological factor and also a factor as to conditions on the planet, is the length of time the communicating civilization remains detectable. FP is the fraction of stars with planets. So we didn't actually know of planets until 1992. Before 1992, planets in other solar systems were just a speculation. Now we know of many exoplanets. What's the most important exoplanet search tool that we have today? Anybody? In 2009, we launched a Kepler Space Telescope, which is dedicated to looking for exoplanets. And it was designed to look for exoplanets using the transit method. And so Kepler is basically just a light detector with a very sensitive light detector that looks for minute dips in the brightness of stars. And about 75% of the exoplanets that we have discovered to date have been from the transit method. And now we believe that planets are the rule and not the exception. Therefore, this factor in the Drake equation is 1. Every single solar system, every single star has planets. The next factor in the Drake equation is NE, the number of planets per star where conditions are suitable for life. It's another question to the audience. What is the most prevalent type of star in the Milky Way galaxy? That's right. Who said red dwarfs? Ken said red dwarfs. That's correct. And about 75% of the stars are red dwarf stars. And the thing with red dwarf stars is that they're small. In this picture to the left, you could see a relative size comparison between the sun and a red dwarf. The red dwarf is the low mass star, even smaller than red dwarfs or brown dwarfs. And you can see that it's almost the size of Jupiter at this point, when you get a little bit smaller than that. And the thing with red dwarfs is that the planets, because of the size of, because red dwarfs are small, planets generally tend to be tidally locked with the star, which means, like our moon, you only have one face that constantly faces the star. And that means you have a star where it's always either daytime on one side, where it's being not prone to, but has light constantly, and one side which is always dark and cold. Another aspect of red dwarfs is that they tend to give off heavy flares. They're considered flare stars. And so 75% of the stars in our Milky Way galaxy are generally not suitable for life, because they're tidally locked and because red dwarfs have gigantic flares. So we already have our first major limitation on the number of potential stars that can form life and can form intelligent life. So let's look at the Earth and Earth's history. So the Earth formed about 4.5 billion years ago. And the first era in Earth history is the Hayden era. And the argument for it being easy for life to form is that we believe that life formed between 4 billion to 3.5 billion years ago. So only about a half a billion to 1 billion years after the Earth formed, we had life already. Plus, in 1952, there was a famous experiment called the Miller-Urey experiment, where the experimenters mixed methane, ammonia, hydrogen, and water in a flask, and they applied electricity to it to simulate lightning. And the result was that they produced amino acids from these inorganic compounds, which made people believe that, well, maybe creating organic compounds in life is not as hard as it might seem. What are the arguments that it's hard? Well, there's no hard evidence that life formed more than once on Earth. Given our 4.5 billion year history, you might think that it may have popped up more than once in different locations, but there's no evidence to that. And one aspect of research that might answer the question as to whether it's easy or hard is whether we eventually find evidence of life, even microscopic life or single cell life, on our other nearest neighbors. Mars has a lot of water. Europa has an active salt water ocean underneath its ice, Europa being a moon of Jupiter. Enceladus has water below an ice sheet around Saturn, and Titan has lakes of methane and other types of compounds on its surface. So if we could find life on these other, history of life on these other planets, even very basic life, we know that it's very easy to form life on other planets. One second. The next epoch in Earth history is the Archean era, which goes from 4 billion years to 2.5 billion years. And what kind of life existed during this time frame? During this time frame, we had single-cell organisms, but not just any type of single-cell organism. We had a very basic type of single-cell organism called a prokaryote. Prokaryotes first appeared between 4 billion and 3.5 billion years ago. Prokaryotes are bacteria and this other type of thing called archaea. Archaea was originally thought to be just exist as extremophiles around very harsh environments, around volcanoes, around the harshest environments on Earth, but now we know that archaea actually exists all over the place. And one key feature, the key features of prokaryotes, unlike a more developed cell, is that there's no cell nucleus and there's no cell organelle. They're just very basic creatures. And then during this period, there was no oxygen in the environment. The environment consisted mainly, the atmosphere consisted mainly of carbon dioxide and methane. So the first billion years of life on Earth, we just had the most simplest form of single cell life, basically simple slime, for 1 billion years. The next era in Earth history is the Proterozoic era, from 2.5 billion years ago to about 500 million years ago. And earlier it said that Brian Cox, who inspired this talk, and others believe that there is a low probability of intelligent life in the Milky Way. And one reason is the first bottleneck in the process. And the first bottleneck is getting to photosynthesis, because oxygen is a very efficient means of for animals to process energy. And at the time, there was no oxygen in the atmosphere. It took something to put oxygen into the atmosphere. That something was photosynthesis. And the first bacteria, the first creatures isn't even the right word, the first things that gave off photosynthesis was cyanobacteria, which first appeared about 2.5 billion years ago. And they produce oxygenic photosynthesis. And oxygenic photosynthesis is a process that releases oxygen as a byproduct of water splitting. And photosynthesis is a very, very complex process. So basically it took, and photosynthesis is required for oxygen. It took about 1.5 billion years from when life first appeared, from the first prokaryotes, to the point where photosynthesis started occurring. And since we only have a sample size of 1, which is the Earth, we don't know if 1.5 billion years to reach photosynthesis is long or short on the bell curve. If we had 100 samples, maybe the average would be 5 billion years for all we know, or maybe 20 billion years, or maybe a half a billion years. But the process of photosynthesis is very complicated, and so some people think that this is a bottleneck that is hard to get over, and that maybe we're just special that we did get over that bottleneck. The second bottleneck that people look at as far as getting from simple cell life to more complex cell life is going from prokaryote to eukaryotes. Eukaryotes are more complex cells. This is probably what you remember from high school biology, where you have a nucleus and you have all these other organelles. And the steps to go from a simple cell creature, the prokaryotes, to this more complex eukaryote was a major, major step in the process. And it took about 2.5, they estimate 2 to 2.5 billion years to get to that point. And the eukaryotes are about 100 times larger than prokaryotes. Eukaryotes have fully formed cells. And it's the same exact cells that are in every living creature, plants, insects, humans. If you look at all cells, they have the same basic structure. So we all evolved from that same common point. And how do we go from prokaryotes to eukaryotes? In a process called symbiogenesis. And the theory holds that all these little organelles in the eukaryote were once bacteria that entered into an archaea cell, and then from there became a host and a hostess. And there was a symbiotic relationship. And somehow, some way, those cells were able to reproduce and expand. But we don't really know how that happened, but we think, again, those who believe that life is on the low probability spectrum see this as a very difficult bottleneck that had to get past in order for the next stage in life to develop. And this process took about 1.5 billion years to occur. I said 2.2 to 2.5 billion years. That's about how long from the start of the planet that we got to eukaryotes. The next major step was multi-cell organisms, which occurred between about 1 billion years ago to a half a billion years ago. And at this stage, we only had our multi-cell organisms were only seaweed, sponges, and basic sea plants. So after 3.5 billion years, 3.5 billion years, just 25% of the age of the universe, we only got as far as seaweed sponges and some basic sea plants and some very simple life forms. The next period is the Phaner, I'm not know if I'm pronouncing this right, but the Phanerozoic period. Who could tell me what happened next? What was the next stage in the history of the Earth? Next stage is what's called the Cambrian explosion. This is where life as we kind of know it first began, about 540,000 years ago. And there was an explosion in the fossil record that occurred around this period of time. And nobody's 100% sure why it occurred. We do know that oxygen levels did increase during this period. About 470,000 years ago, we had the first real land-based plants developing. And 400,000 years ago, the first land animals started to appear. So we're talking about 3.5 billion years before life starts to really get complex. About 200,000 years ago, during the Jurassic era, dinosaurs dominated the planet. Question? Yeah. No, that's 200,000. Oh, I'm sorry, 200, you're right, I'm sorry, 200 million. Thank you, I'm sorry. I said that, yes, I'm sorry, 540 million years ago, 470 million. That's K, I guess, yeah, that's supposed to be millions, sorry about that. Thank you for correcting me. Okay, so is intelligent life inevitable? So another question for the audience. What major event in Earth history was a but-for cause for intelligent life? What's that? Yeah, yes, meteor. Thank you. 66 million years ago, we had the KPG extinction event. An asteroid about 6 miles wide and traveling about 12 miles a second hit the Earth. And without that event, we wouldn't be here today, because that event enabled the rise of the mammals, the creatures from which we evolved. Now, when I first started looking into this topic, there was some people who had said that the KPG event, the asteroid that hit us, was really a 1 in a million event. Without that 1 in a million event, it may have been another 500 million years of dinosaur existence, or maybe another 10 billion years of dinosaur existence. Now, people say it was a 1 in a million event because asteroids of that size don't hit that often, or that was what they at least thought. And it also hit at a part of the Earth, the Yucatan Peninsula, which contained a lot of sulfur. So the first, but upon further research, there's been a little bit more developments and nuance and discoveries with respect to these, to what happened during the KPG event. Some people, the most recent research is that these size asteroids can hit the Earth about once every 250 million years. It's not exactly a 1 in a million event, but it's a rare event and didn't necessarily have to happen. And the dinosaurs could have kept on living on the Earth for many, many more years before the mammals rose, if ever. And the same thing with the sulfur effect. So initially, sulfur had two effects in the post-KPG era after the asteroid hit. It resulted in acid rain, and it also resulted in a cooling effect, an anti-greenhouse effect, which made the planet much cooler, although the sulfur effect now is believed to be less impactful. But this still shows that we're at the mercy of events in order for life to take the next stage. We could have gone another 500 million years, or maybe another 5 billion years before intelligent life, if ever, arose. There was also what made the KPG extinction event also more of a rare event was that just by coincidence, at the same time, and it's debated as to the impact of this, but there were extensive volcanic activity on the continent of India going on, which is called the Deccan volcanism, and that may have also contributed to the extinction of a lot of the Earth's animals at that time. So as we could see, it took us 4.5 billion years, 1/3 the age of the universe, to get to where we are. And you might wonder, it's not just about having a large brain that enabled us to develop technology. Other animals have large brains as well. The sperm whale has the largest brain on Earth, then elephants, then orcas, and then bottlenose dolphins. But whales, orcas, and dolphins don't have hands, they don't have fingers, and they live in the ocean. So intelligent life might develop, but then they might not be able to communicate or do anything with that intelligence. Elephants don't have the type of locomotion and hands and fingers that we do. So this brings us to the next factor in the discussion, which is the fraction of intelligent civilizations that can produce communication technology that we can detect. And this is a segue into SETI. And again, as I mentioned earlier, Frank Drake was responsible for the first launching the SETI program with radio astronomy. And we used the 1420 spectrum, which is reserved now for research purposes. In 1977, we had the most curious data capture of our SETI history. And it's called the WOW signal. And this was a strong narrowband signal at the frequency 1420, detected on August 15, 1977, by Ohio State University's Big Ear telescope. The signal appeared to come from the direction of Sagittarius. The entire signal lasted 42 seconds. And despite numerous follow-up searches, nobody's ever been able to find another signal like that in that location. And they've kind of ruled out a lot of other potential non-extraterrestrial sources, such as deep reflections from space debris. It wasn't that. Interstellar scintillation, comet, hydration clouds. So we believe it was extraterrestrial, but we've never been able to replicate it. And so it's just left out there as a big mystery. And who funds SETI? Well, in 1992, Richard Bryan, former Nevada governor and then U.S. senator from Nevada, made this statement before the U.S. Congress. As of today, millions have been spent, and we have yet to bag a single little green fellow. Not a single Martian has said, "Take me to your leader," and not a single flying saucer has applied for FAA approval. And so basically, SETI research got killed as far as government funding goes because it wasn't because of people who didn't believe in the project. So SETI today relies on private donations, mostly from high net worth angel investors. In 2007, the most extensive SETI array was the Allen Telescope Array, which was supported by Paul Allen, co-founder of Microsoft, with a $30 million project donation. In 2016, Yuri Milner, a scientist and business person, donated $100 million for the Breakthrough Listen system. Yuri Milner was born in the Soviet Union and then moved to the US. Yuri Milner was named after Yuri Gagarin, the first person in space. He spent his life always loving space and technology. This is the Green Bank telescope is the world's largest steerable radio telescope. It has a sensitivity to detect Earth leakage, like when we have radio signals from Earth, from stars within 5 parsecs. 5 parsecs. 1 parsec is about 3.3 light years. It is estimated that the project will generate as much data in 1 day as previous SETI projects generated in 1 year. And will cover 10 times more of the sky, at least 15 times more of the radio spectrum, and 100 times faster. What's that? Yes. And in 2020, China went online with a 500-meter aperture spherical radio telescope. And this is a comparison with the Arecibo telescope in Puerto Rico. You can see how much larger the China telescope is. So, we've got all the tools in place to hopefully maybe make a breakthrough in SETI research in the coming years. The final factor in the Drake equation is the length of time the communicating civilization remains detectable. And these raise sociological considerations. Do advanced civilizations last forever? Some point out that even if the Greek and Roman civilizations faded, technology still continued, so it shouldn't be that much of a factor. But there is inherent violence in nature. Animals fight for food and they fight for a mate. This propels natural selection. And so this creates a barrier. Does our inherent weaknesses and limitations create a barrier to longevity? And we just have to look at this 20th century history to wonder. In the 20th century, we had, major developed countries go to war twice. And then there's our own planet limitations. Natural climate change occurs. 15,000 years ago, where we stand right now was under a mile-high glacier. And in another 15,000 years or 20,000 years, that mile-high glacier might be back. And about 600 billion years ago, Earth turned into a snowball because of climate changes. There could be resource limits, overpopulation. The famous case of Easter Island, where they had an island of 15,000 people, that by the time Western civilization found them, they were down to 2,000 people because of limited resources. Disease, we just went through COVID-19. External forces exist, asteroid impacts, gamma ray bursts, supernova explosions. Well, good news, I did meet an alien recently. I got to take a picture with him. Actually, this is in Niagara Falls, and there's a great restaurant there on the Canadian side of the falls. And if you ever get the chance to go to Niagara Falls, do it. It's a beautiful place.